So, welcome everyone to the second lecture of the lecture Statistical Learning for Statistical Theory for Deep Learning. And well, as a producer I can say it's still not working completely, but it's working better than the last time. I have Wi-Fi, but somehow now the sound is not working properly, which I don't understand, but okay. That's the life as a producer. I brought you with me a slide where I repeat some of the things from last lecture. Maybe I look at it in this way. The last lecture I defined deep learning as a collection of methods which fit deep neural networks to data. And I told you there are two reasons why this is so successfully in the modern times, because there are huge data sets available and the computing power has been massively increased in the last years. And then I introduced already the first type of deep neural networks, namely the feed-forward neural networks, which use a simple model of nerve cells by some function which makes a kind of thresholding of a linear combination of the input. So you define a function f of x with, or f of inputs O1 to OD by activation function sigma applied to weights W0 plus W1 times the first input plus, and so on, plus WD times these input. And for this activation function, you can use, for instance, a smooth function which makes a kind of thresholding, which is the logistic threshold sigma of x is equal to 1 divided by 1 plus e minus x. Or you can use what is nowadays the most popular one, the so-called ReLU activation function, sigma of x is the maximum of x of 0. And then you have a simple function and you make a network of this simple function, and this network can be recursively defined, and I defined it here as a function f with index w. W is a vector of weights. On the last layer, it's just a linear combination of the outputs of the else layer, and then the small else layer is recursively defined as activation function of the activation function applied to the linear combination of the outputs of the previous layer. And for the first layer, we just use activation function applied to a linear combination of the components of x plus some bias value. And here you have this activation function, which is the parameter. You have the width of the network, which is here. How many neurons do you have in each layer? And you have the depth of the network, which it's capital L, which tells you how many layers do you have. And then we have defined the space of function f capital L small r, which is the space of function of all fwv, where fw, where w is one possible, that's great, where w is a possible vector of the, should come back again in a second. Oh, it doesn't come back. I like this. Let me make it first here. Capital again. Okay, let me see it again. Where W is the vector of our weights, and you have K, capital K weights, and you can count them. I have no formula here. And this is the space of all feed-through neural networks with depth L, with R, and activation function sigma. So as soon as you I give you an activation function, I tell you what capital L is, and I tell you what small r is, I have defined a set of functions. And this is a new way to define a set of functions. And then you can say, okay, is it important to define a set of functions? Well, depends what you are doing for your life. If you are, as me, a guy who works for approximately 30 years for curve estimation, then defining set of functions is a great idea. And if you come up with a new way of defining a set of functions, you can use it in statistics in many different ways. As you will see in this lecture, in future lectures. So that's the big thing. To say it in some other words, what this is about, or what I mean here, is I can tell you about Step Up Miami Heat. I was once in the cinema, I have seen Step Up Miami Heat, because I've promised my, at that time, au pair girl, that she can choose any movie which she has, but she has to look at it in German, so that she can improve her German. And then she came up with Step Up Miami Heat, something which I had no idea she was running in the cinema. But then I was sitting in Step Up Miami Heat, and it turns out it was well, as if you know the Step Up movies, it's about a group of young people dancing for life. And the most important thing in this movie was to come up with the right move. If you have the right dance move, then you will change the whole world, basically. That's the idea. I would say if you are a guy in curve estimation, then if you come up with the right function space, then you change the world. And that's a great idea. Okay, first thing. Second thing which I could try to show you, this lecture is about deep learning, and I could try to show you deep learning in practice. My favorite application here, and it should be here. If we make this, can I make this large? Why can't I make this large? Because I have no idea where this. Why is this window not? No. Oh, here it is. Let me make this window large. Then you see what I'm doing at the moment. You see it here, yeah. I have an iPhone in back, and it's it's recording the lecture, and I don't need to show it you here because you see it also on the projections, and then I open QuickTime player on my MacBook, and I feed in the image from the iPhone, and I can record it. And the idea would be that I also feed in the sound from the microphone, which I'm doing here, but unfortunately it doesn't detect at the moment the sound. Oh, okay, so I have to use my regular sound at the moment, which just records, puts the microphone over here, which is not perfect. But where does deep learning comes into play? Well, what I can do now is I can turn on. I go to the settings of the camera, it's here, and I turn on mode. And then it should, and it's not working. Okay, but you know, I'm a mathematician. A mathematician does not give up so quickly. We just changed it here. That's the follow mode, and let me zoom in more to me at this point, and then turn on the follow mode again, and let's see whether it. Now it should work. Okay. What this usually does, it follows the speaker, and that's so it automatically detects where the speaker is, and then it zooms in on the speaker, which is absolutely great. Yeah. If it's working, and it's not working currently. Okay. I don't know why. Well, is this great? We can think about it, but let me go back. I have to change the resolution to the proper resolution so that I make a. Why do I think this is great? Well, if you think about it, each idiot can do this here. I can ask any guy, and hire him and pay him some money, and he will sit in the back with a camera, and then of course he can zoom on the speaker. We don't need any big skills for that, but the point is, clearly a computer, or up to a few years ago, a computer cannot do such things. And that's typical. that you have, and well, that's typical for like few years ago, let's say 10 years ago, 15 years ago, the computer was able to do very complicated things, maybe solve some very complicated, very large linear equation system. But on the other hand, he was not able, or it was not able, to perform some task which each human can do. Children can do it easily. Or if you think about you show children a picture of a cat and a picture of a car, and then it should decide where the cat is. Of course, it can immediately decide where the cat is. But you show a computer a picture of a cat, a picture of a car, and want him to decide about this. No idea here how it is doing. But the point is, with this deep learning, these computers are trying to do exactly this. And that's what we talk today about. So let me maybe turn off the beamer here because I don't need it anymore. Turn on the light maybe a little bit. And then, and one great achievement in the past was that the computer was able to understand images. And the reason behind this or the major progress in this, it was before also a little bit, but then came the major progress, and the major progress was with convolutional neural networks, what we talk next about. So we come to section 1.2, convolutional neural networks. And what I want to explain to you now or next is we have this idea how to model functions which get some sequence of real numbers as an input and produce some output. How you can produce from this idea functions which get some image as an input and produce some output. And if you can do this, then you can, for instance, use it to predict the probability that this image shows a cat or a car, something like this here. So the whole thing is that we now no longer apply it to a sequence of numbers. Instead, we apply it to an input which has some structure. So the convolutional neural network. I will use the shortcut CNNs. CNN for convolutional neural network are applied to input with structure. For instance, images. That's the main application. And I will describe an image by some matrix with dimension d1 times d2. d1 times d2 dimensional matrix. And this matrix has entries which, and I make it simple, I just make black and white images, no colors. So you just have to describe for each pixel of the image, d1 and d2 describes the resolution of the image. I describe for each pixel the grayscale value as a number between 0 and 1. So that's in 0, 1, which I call white as this exponent d1 times d2. where the input follows entry. And position ij, and I use for this position input, I use the notation x index ij at position ij. And that's in I is one number between 1 and d1, and j is one number between 1 and d2. This describes the grayscale value of the image at position 1, d2. And next I want to define a neural network which can use such matrices as input. And of course, you can just forget about the structure, d1 times d2. You just write the whole thing in a long vector. Then you have consider the input as an element in R with exponent d1 times d2. And you apply a normal feed-forward neural network. Do you have any idea why we don't do it in this way?
I guess it would be that for images, we don't only need one pixel, but the surrounding pixels. So we need some kind of connection between them.
You don't need just one pixel, you need a surrounding pixel. But if you have the whole vector of all values, yeah, then you can find this neighborhood by yourself, yeah, because you don't have to use non-zero weights for all connections, but just one of them. It's not a problem. That's not a major problem, but it goes in this way. Any other idea? Well, think about what are typical values for d1 and d2. Honestly, I have no idea, but maybe, or I don't know it exactly, but any idea how large d1, d2 is?
When you take in normal standard criteria, I get like 1,920 times 1,080 or something, and just get.
So you get something like 1,000 and like 1,000, so 1 million could be the size, yeah. And if you have seen this slide from me at the very beginning, and I have handwritten this slide, and then I scanned it yesterday on my computer and uploaded it, or showed here the PDF. And when I scanned this PDF, it got the size of about 2 megabytes, or 2.5 megabytes. But it was with colors, so it basically has 3 values for each pixel, giving you the values for the scale on 3 different colors for this same color. But you are close to 1 million here, and that means even if you just start with 1 neuron in the first hidden layer, you already need 1 million vector or values for 1 million weights, which is the kind of problem. But of course, you could make it much bigger. And that's the reason why you don't use this. Instead, the shrinks for ZNNs are the following. First, we basically make a feed-forward neural network, but we arrange the neurons in we arrange the neurons in planes where the planes have positions, and the position corresponds to the position of the input. with positions. Corresponding to the positions of the input. So for if I look at the hidden layers, then they have some index by the position, and then for each index I have not only one neuron, I have several neurons, and then I connect. Well, moment it doesn't happen if I just rearrange it, but the trick is now I connect the neurons only to those neurons which corresponds to positions which are nearby. So this is a kind of sparsity. Okay, connect neurons only to neurons from the previous layer which correspond to positions close to it, to the position. Which correspond close to the position of the neuron. First trick. The second trick is, what are you doing with images? Well, for instance, if you want to detect the speaker of your image, where's the person in the image, then you can search out parts of this image and look whether there is a speaker there or not. And for this searching, you can use different neurons, of the hidden neurons, which corresponds to some position, and you can look at this feature there. And if you look at one position and the other position, then basically you can use the same weights. So what you are doing, you share weights. So weights are shared. Or more precisely, I use the same weights for neurons which correspond to different positions. Weights to different positions. And again, you see, this reduced the number of values for the weights which you need drastically. The first one already reduced it because you have this position only close to, all the others are 0. And now you say, okay, the dimension of the image is no longer so important for the hidden layers, because on this plane you use on each position the same weights. And then there's this third thing. You use additional layers, different from the standard feed-forward layer, which makes some kind of pooling and subsampling layers. And what I mean with this, I will explain later. Okay, that's the idea. Now the question is how to describe it mathematically. So mathematical. This can be described as follows. And here I just give one possible example, and you can do it in different ways. So I start with my input, and I denote my input as a output of the series layer to write it later on recursively. So I have an output. It corresponds to a position on the series layer. And I have several neurons for each of the position, but of course for the input I have just one neuron. And that's my xij. And my ij is in a set of indices. That's d1 times. Then I compute a number of convolutional layers, and here I just compute once convolutional layers, and the number of layers is capital L. So I define an output of the Lth layer, and now small l, and L runs from 1 to capital L. It has a position, as before. And it has, I have several, now I actually have several neurons for each position, and the number of neurons is K sub L, which I have, and the number I consider here is the number S2. And I make this for S2, 1, 2, 3 until sub L. And then the whole thing is, well, it's your activation function applied to a linear combination of the previous neurons on the previous layer. And I want to tell you, okay, we don't want to use all neurons. We just want to use neurons which are close by. So I don't go connect to all values I prime, j prime. I just connect to values which are close by. And then I want to use the same weight for this connection independent of what I and j is. And I connect it to all other neurons at these positions. And these are the neurons for the channel, so I connect it to all channels. And I make this by saying, okay, the number of the neuron is S1 corresponding to position. This runs up to some k L minus 1. And I sum up over some weight with some index. And we will think about what the proper index is for a moment. That's WL. There should be a lot of indices here. And then times the output of the previous layer and proper indices here. And now you have to think about what do I sum here up. And I also want to share these things. So I do this in a way that I just add to my position some offsets. So I'm making here an offset T1 minus 1, and I add an offset to J T2 minus 1. And okay, and that's the end of the blackboard, which is bad, because of course I need a value as 1 here for the channel number. And then you see here I need a T1 and T2 have to run as a symbols. I have to T1 and T2. That's are the offsets. Yeah, and it's too small here. Okay, forget about it. Let me write it here again, because the number of indices. You have to be careful about the indices here. Sigma off. You make this number of channels. You have KL minus 1 neurons in the layer L minus 1 before layer L. You sum over T1, T2, and I could make it symmetric around 0, but I make it not symmetric around 0. This depends on what you like more. I make it until some filter size, and that's here in capital ML. And then you have the weight. And the weight now depends on, well, of course, it has to depend on not the position, but it has to depend on T1, T2. And it has to depend on the channels you are losing, S1 and S2. And you combine with the guy over there. I plus T1 minus 1, J plus 2 minus 1. And this was an S1. And now you have to be a little bit careful, because your indices corresponding to this position on the L minus 1 layer must be such that this neuron for this position really exists. So you restrict the sum here by saying I plus T1 minus 1 and J plus 2 minus 1 must be in the set of indices. And that's it. And that's your formula. And that's doing what first and second is describing. Where? So what do we have? We have Ij in L, Ij in D. You have L in 1, 2, I'll say S2 before. That's S2 is one of the number of neurons you have. That's KL. And L is in 1, 2. Well, and now this K1 or not K1 but K0. K0 will be 1. And K1 to up to KL, capital L, are natural numbers. And these are the number of channels. And the number of channels just described how many neurons you have in the hidden layers for each position. the M1 to ML, they described how far you walk around your position. And I use here values starting from 1. And it's clear you should end, you shouldn't be larger than D1 or larger than D2. So I stop at the minimum of D1 and D2. That are the filter sizes. And of course, all these weights are the weights of the convolutional layer. Question, please?
So within one layer, the position of this neuron is dependent on the for once an index between 0 and the number of neurons in a layer. So there's Ki or K.
It's 1. It's 1 and the number of the neurons in the layer. I start with indices 1, 2, 3 until KL. Okay, L minus 1. And the other one is the position.
And the other one is the position.
So you arrange your neurons in planes, and for each position you have, in the else layer you have KL many neurons.
So instead of basically one layer being a row or column, it's being a matrix.
It's the matrix.
Oh, well.
Well, I remember when I was writing my first paper about convolutional networks and the statistical theory, or about it together with a colleague of mine in Montreal. And then we were working together for 1 week. In this week I was fighting with the proof all the time, and he was fighting with my notation. So I was trying to understand the proof, he was trying to understand my notation, because that's terribly complicated. But if you think about it, it's totally trivial. Yeah? It's just a neural network where you rearrange your hidden neurons and give them additional index with the position. That's it.
Could you maybe repeat what the channels are? I didn't get the example.
The channels is the number. So the channel 1 to L. So basically, you have KL channels, because for each position you have KL neurons. But now you can consider it, because it's as you said, it's a 3-dimensional thing, yeah? You can also consider it different. You can say, okay, I consider a channel, and for each channel I have a whole image, or a reconstruction of my image, or a new representation of my image, maybe. You can also look at it in this way. And then you understand why it's called channel. More question, please?
Can I think of channels as layers in a neural network?
Can you see of channels as layers in a neural network?
Because there's also the position, which is the matrix, and there I would say that it's the layer of the
It's a layer. No, the layer is 3-dimensional, yeah. And then if you have something 3-dimensional, yeah, you can reduce it to you can fix one of its components, yeah. And if you fix the last components, then this is a channel.
So the whole thing is one.
So the whole thing is 3-dimensional on your 2-dimensional image, yeah. It's 3-dimensional, yeah. And now I can say, okay, well, what I have basically KL many different neural networks on top of it. But they are connected in between. You see, I don't only connect channel S2 with channel S2, I connect it with all channels in the previous layer. That's a tricky. Okay, and now one more thing, and then maybe I write it here. Maybe I don't write it here. Finally, we apply. No, I'm losing, yeah? Okay, maybe we make a break and I clean some part of the blackboard over there, and then I can write the other thing because you have to see the thing at once. So it's now 10:33, so I will go on around 10:38. Okay, I would like to go on. I've forgotten, of course, here, sigma is the activation function. For instance, I can use the Relu activation function. Maximum x0 is the activation function. And in my example now, I just make one pooling layer, and then make a so-called global max pooling layer. Global max pooling layer. So I say that my function value, depending on my values w, my and I forgot here something, sorry for that. Do I have some color here? It will be over here. Well, not here, so I have to make it without color. Because you would have to add a bias here, of course. And this bias depends on, yeah, it doesn't depend on the position here, of course. And IG need just one bias, so it doesn't have to depend on S1. So the bias just depends on S2. And the layer. And then I define my function, which depends on this weights W index T1, T2, S1, S2. It depends on the bias weights. Bias, and it depends on some additional output weight, which I will use next. Out of X. And I just make the maximum. Well, after the else layer, I make for each position, I make a linear combination of the outputs of all positions below. So you have the position is, you have these channels S2 to KL, any channels, KWL, WS2 times output of layer L. position j and channel number S2, where ij runs either through all positions, or I can also restrict it, and I restrict it here to P1 minus some capital B plus 1. That's different from the lecture notes. That I use here B2 minus capital B plus 1. And B could be, for instance, 1, and then you have no restriction, or B could be greater than 1, then you forget about some of the rules at the border. And where, so B, the output bound could be 1, then you just make a position over all things, but I can also make it larger. The minimum P1 and 2. It's the algebraic bound. The W are all these weights which I use for my filters. So these are this W T sub T1, T2, S1, S2 with our bound L. So now you can see what T1 is running from. Here's a ij, which is wrong here. So T1 is, and T2 is from 1 to an L. And S1 was from 1 to k minus 1. S2 from 1 to k up. And L was from 1 to capital L. So the bounds and here is typing error in the lecture note, which I have to correct. Oh, well, I wrote this by makes more sense. Then the W bias are all my bias weights. So these are the WS2L. And S2 is running from 1 to KL and L from 1 to L. And in addition, we have the W out. And these are just the WS2. And again, I have defined a function space depending on a function which these weights, and depending on a lot of parameters which you see, which are, well, how many convolutional layers you use, how many channels you have in each layer, here depths, and what are the filter sizes. That's are your parameters. And as soon as you have fixed this, you can let vary all course, you can do many modifications here. Oh yeah, or here's also written maybe to the output of this convolutional neural network, then you apply a standard feed-forward neural network to make more complication. But I ignore this here. And also you can use some, instead of just using finally a global max pooling layer, you could use in between the subsampling layer or local max pooling layer. We could insert one or many subsampling layer. And what do I do with the subsampling layer? Well, it reduces the resolution of the. So what you compute here are representations of this, or you can say what you compute here is on each layer you computed representation of the original image. And you have as many as representations as you have number of channels. Now you can start to reduce the resolution of your representations in between. Because you say you want to look whether there is a cat somewhere in the car, then you look at first whether there are at some position whether there is a head of a cat, another position whether there is a foot of a hat, and whether there's a tail of the hat, and then you combine the whole things. Yeah? But as soon as you have detected at some position the hat, then you don't need it for all positions. You can reduce the resolution, and this can be done by choosing some R. 1 to minimum D1, D2, and Z. So I subdivide my whole image into some patches, and from each of the patches I just use one of the entries. So I define O J L and channel number S2. As the one position L minus 1. And now I replace, I use also S2, the same channel, but instead of position I use position 1 plus I minus 1 times R, and instead of position J, I use 1 plus I minus 1 times J minus 1 times R. That's 2. And then J doesn't run from 1 to D1, 1 to D2, but just such that this indices here are still in the original, original positions. So you get my J actually in 1 divided by R, which doesn't have to be a natural number. So I make a ceiling. So I go to the next natural number. If it's not a natural number, then be 2 divided by R. And that's my new indices D prime. Make this at some layer L. And use D prime instead of D from that layer on. after this layer. So you forget about a lot of values which you have computed, and but the advantage is that your whole image, or the representation of the image, gets smaller, and maybe they represent the image on a higher level. Alternative is to use a local max pooling layer, where instead of just choosing one of these values locally, for many values, you choose the maximum of them locally. Local max pooling layer. And I don't want to give a definition here. You can imagine how to do it. You just you see here from some square of possible values which I have computed. I just choose one of them, and the one at the lower left corner. And instead, you can just choose from this square the maximum one. Would be a local max pooling, corresponding to this global max pooling layer. But here in the global max pooling layer, you also have a linear combination in addition. So you learn all the channels, which you don't do for a local max pooling layer. And of course, there exist many, many modifications of this. And then there are some people coming up with some new topology for convolutional networks applied to some data and show it works better than the other one. Okay. Questions?
So when you say topology, you mean how the layers are structured, not the word topology.
In topology, for a neural network, it's just what are the layers and how many layers do we have. Yeah, not nothing to do with topology in the network. Sense. That's right. Other questions? So what you have learned now is how to deal with images. They have some grid-like structure, and you just rearrange the neurons according to this grid-like structure. You use some kind of symmetry in the weights to reduce the total number of weights you have, and finally to use this global max pooling layer. Okay, then I quickly have to clean some part of the clipboard. Maybe over there. And we have just seen how computers can deal, thanks to deep learning, with images. And next, we see how computer can deal, thanks to transformer networks, with language or human conversation. That's the next big step. Transforming. This is also something which is very easy for humans. They can understand some language. Well, not so easy if you, for instance, translate to another language or something like this. And it's not so easy if this if you're given a lot of big text to look at, to extract things. But if you think about 20 years ago, computers were not able to do it at all, or not good at all. Yeah. 30 years ago, people were trying to come up with some ideas how computers can automatically translate from one language to another, and it failed totally. With reasonable results. And today you have it. You can do it. Even your smartphone can do it. If you download the right app, which is fascinating. Again, you have some data which have some structure, but this time it's, the structure is that it consists of a sequence of data points. So transformer networks. Data. Sequences. And what I consider in the sequel is text data. So I have some written text. Could be also some text which is spoken, but then you need something else to transform from spoken language to written language, which is nowadays not so difficult to do. So I've given you a long written text, and the computer should be somehow able to deal with that. And for this we want to use again neural networks. And then the question is, we have the text, we have the neural network, how to apply the neural network to the text there. Because the neural network is applied to vectors of numbers, not to a collection of words. Okay. The first step is that we transform the sequence of words in sequence of real numbers. First step. Words. Sequence. Real numbers. And then we have a new representation of our text, and of course, to this sequence of real numbers, we can apply our standard neural network. This is a word-to-vector conversation. Conversion. And there are algorithms for this. And what you do, for instance, you tokenize the text. And you can think of tokens of something like words. So you detect where does the word start, where does the word end. Is this difficult? Well, a little bit, because there could be something like comma, dots, points, and so form of this?
Semicolon.
Semicolon and so on, yeah. No, I see these two dots. Colon? Colon. So, and this is not so easy to detect if you want to distinguish, for instance, from description of date. But you can do this nowadays. I don't comment on that. So you have a token. Then you learn shared subword units. You start with a list with a simple vocabulary, which contains all the symbols which occur in the text, including the letters and so on. And then you successively extend it by looking at those pairs of symbols which occurs most frequently next to each other in one of your tokens in the text, so within the same token. You merge them and replace them by a new symbol, which you add to your vocabulary. And you do this recursively until you reach a reasonable size of your vocabulary size, and the limit would be something like 32,000. So recursively, place the most frequent occurring pairs of symbols pair of symbol within the same token by a new symbol until the desired vocabulary size is reached. Very nice. And that could be, for instance, 32,000 is reached. Then you stop. Then you have a new vocabulary, and this new vocabulary are subwords which occur in your text. So no longer words, but subwords. And a lot of them. Second point. And then you assign each of these subwords to some vector of real numbers, high dimension. Then assign each subword to a vector R with exponent d model, and the model is something large. It's not just 1 or 2, but it's something large. How do we do this? Well, you can use, for instance, just do it randomly. Because with these guys you will go on, and from these guys you will make some kind of transformations, and you learn this transformation within the transformer. So you can start with something reasonable, or you can also start with something randomly, as long as they are different. Alternative, you can say, I did this already in the past. And I have some pre-trained model where I made this in some reasonable way, and I use this pre-trained model. But random values will work. And then we have transformed our text consisting of L words in some, or we have confirmed our text in some sequence concerning of some L of these vectors. And that's what we assume as input from now on. Let me try with the new one here. So from now on, I assume that each data point we assume that our data or given data or given input of the network is of the form X. We have L of our shared subwords, and each of these shared subwords is mapped to some vector in R with exponent T model. So the whole thing is we have L of these vectors. So we have something in R with exponent T model times L, which is huge. Because the length could belong from our text, and the model is huge. But I have now a sequence of numbers, and I could apply a standard feed-forward neural network to it. Now, why don't we apply a standard feed-forward neural network to it? Do we want something else? I could say I'm finished, yeah? No, my function space is just a set of feed-forward neural networks applied to R with exponent D model times R. And I feed it to data.
But usually it's because computationally it's just too expensive.
Computational is too expensive, correct, but why?
Because we don't use the structure that we know of the data.
We don't use the structure that we know, and why is this a problem?
Because the network will be too hard to train.
And yes, the network will be too hard to train, but why it is hard to train? Why can we train it?
It's too large. Maybe.
It's too large. The input is too large. The input dimension, the model times L will be huge. The length could be large, the model will be large. Not a good idea. Basically, it's the length which comes in addition. To think about you giving what what you think about ChatGPT here. You enter some text and ask maybe, give me the main arguments in the text, yeah? Then the L won't be 1 or 2, yeah? It could be 1,000 words or something like this here. It will increase. And as we said, we didn't use the capture. So the model times L will be too large. To apply a standard feed-forward neural network. And now the standard idea until 2017 was to use in this context instead the so-called recurrent neural network, which is one of the xi after the other, then makes a computation based on this xi. It gets some output, but it uses this output also as input when it sees the next one. And it's a kind of machine which you let run through your text, word by word. Possible solution. Use recurrent neural network. And I don't give a formal definition, I just make you a picture. You have the neural network. You get the input. You get the output. And from the output you also send something back to the input. And here you present x1 to xl sequential. And I could give you a definition, but it's not so interesting yet. I would make these outputs depending on the time and make some recursion. And that was a little bit successful, not totally unsuccessfully. For instance, it was able to come up with some automatic translation between languages, which you could actually use in practice. But if you present the input sequentially, you have a problem. Think about the following example. I give you the following sentence. I do not like the sense, this bank. And you want to transfer or translate it in a different language. Then it's not difficult to translate, I do not like this bank, and I do not like this, but this bank has several meanings. So you have to decide about the meaning. And in order to decide about it, you look in the context. And the context is, the reason is that each time you still have no idea, but I could go on until you walk into it. There's a long queue at the counter. Queue. At the counter. and then you know it's the company where you have your money and where you can withdraw some money. Or the sentence could go on, the reason is that each time I sit on it my back hurts. And then you see, you have to see this word, 1, 2, 3, 4, 5, 6, 7, and still you don't know what the meaning is. You have to remember everything until the 8th word at least. And I can make this arbitrarily large, this can be if I want. And that's the problem of this, for this kind of networks. And then there was some idea, a so-called attention mechanism, to extend this recurrent neural network by something additional. Instead of this structure, you computed the output in a new way. And then it turned out this additional is enough. You don't need this recurrent connection anymore and so on. You can forget all about this. And this gives you the transformer. Any questions? Please.
I have a question about the word to vector conversion.
Yes?
Why do we make such a big deal out of it? Why don't we just, there's maybe 50 symbols that appear in the text, 50 different symbols, and we assign each a natural number and do it that way? Do we kind of teach the model what syllables and longer and even words might be?
Well, maybe it's not enough just to have the symbol, because it's better if you it's a good point. Why don't we just use why doesn't this network learn by itself what the pairs of symbols are? The important one, yeah. Yes.
I think is it just to help it generalize, maybe when I add a letter to a word, that it can learn what that is supposed to do, instead of having to learn it the hard way for all the combinations of letters?
I don't know, but I think it sounds reasonable what you says. I think there's some kind of idea here that if you it should also work if it sees text which it has not seen before yet. And then maybe these subwords will, of course, letters will occur too, but maybe you lose information here if you just get as an input the individual letters.
If I understood the question correctly, it was why we don't just enumerate the words and that's it?
No, it was the letters, yeah. You want to use the words or you want to use the letters?
Letters and symbols, like
Letters and symbols. Symbols,
So
yeah.
you could also enumerate the words. I don't think it makes much of a difference.
Oh, yeah, the difference will not make a big difference because in your vocabulary which you have, maybe some new word will occur here. And then you don't, if you have never seen this word before, you have no chance to predict something like this. That's not just working. Or your text might be too short, which you use here, yeah. This will work also if you get words which you have not seen in your original text, which you use for training, which is great, yeah. And he was proposing just to use symbols from the very beginning. They don't merge them yet. But I think that's I guess then you have to learn more.
So I think maybe it would help if, for example, because I feel like now I make RD model, I make that dimension very high, but then maybe the length goes down because it knows the words. So if I enter a text that has 5 words and it knows all the words, then it's only 5 long, the sequence, and not, I don't know, 20 letters, because it only knows the individual letters. And I have to.
Okay, but what would you want to? But we are maybe already at the end, so maybe we discuss this the next time if you want to post it again, something like this. I don't want to talk longer than 9 90 minutes here and steal some of your time. And I can also think about the question. So, thank you very much.